All all right. Thank you for coming this fourth day of this workshop. It's my great pleasure to be the chair of this session. Introduce our keynote speaker, Tom Nichols. Tom is a professor of neuroimaging statistics at the Oxford Big Data Institute. And Tom is one of the leading figures in neuroimaging statistics, is our role model. And he published numerous papers, high-impact papers, and I think one of the facts I want to mention is that when Tom was a student or junior faculty, published several papers now with citation over 5,000, I think. And I think this is something we need to think about or to learn from Tom. Okay, but without further delay, let's welcome Tom to give our keynote speech.
Okay. Thanks, Jen, and thanks to Hung Tu and Jen for putting this all together. I really enjoyed this week. So apologies for people that were at the neuroimaging workshop in Seoul. This is largely the same talk I gave there. Just a few, I'm not going to do the 3 questions, but I thought I'd take the opportunity to do just a couple announcements. So to advertise, we will be doing another neuroimaging workshop in Brisbane, Australia, where the next OHBM is going to be. Still figuring out it's going to be before or after, but just keep posted, and we'd love to see you there if you are going to HBM, or maybe just come for that. The other one is just I am at Oxford. I'm at the Oxford's Big Data Institute. It's a center for sort of biomedical data analysis. It's a crossroads where all the sort of the stats and engineering nerds meet up with all the medical people. We have a graduate training program. So if you are in a situation, someone who's in Europe or wants to go, we are in the unusual situation. We have a small number of slots that we can fund overseas individuals. It's one of the few good things that came out of Brexit. Yeah, we know people that are interested, please put them in touch with me. And then just the third is that I'm on the editorial board of yet another journal that's being started. So the Royal Statistical Society has just created a journal on data science and artificial intelligence. So yet another venue for your work. This is just being opened, and yeah, you can find out more about it there. Right, so my goal is to talk to you about longitudinal neuroimaging. It's something I've been really interested in for some time. Early on, there wasn't any longitudinal neuroimaging data, so there really wasn't much for this for this work to get purchased. But finally now there are more and more studies collecting longitudinal data. So I just want to briefly sort of motivate, why is this kind of a nuisance? Why can't we just use the established tools? Pause and talk a little bit about novel building. If you have not done anything with longitudinal data, you may not sort of be aware of this kind of really important need to separately consider longitudinal cross-sectional effects. And then I will talk about 3 different projects I've been involved in that have tried to address this need for neuroimaging. So for this audience, I probably don't really need to say this very much, is that, why is this data annoying? Well, is that it is annoying because the data are not independent. The areas we were just to sort of fit this main effect here, of course, all the red subjects residuals would be positive, all the green subjects residuals would be negatives. There would be sort of dependence in here. So you have to model that. And once you do, you then get these 2 different sources of variation. So you can no longer just use ordinary least squares. You need to use a model that fits random intercepts, as well as slopes, and possibly more complicated things. And to this day, there are people in neuroimaging like, you can just use linear regression. You can just patch it up, or maybe throw in some fixed effect intercepts for each individual, which is, it turns out there's some very special cases where that works, but in general, it does not work. So it's just important that you cannot use the standard methods to address this. It will generally have inflated significances when you ignore this positive dependence in the residuals. Okay, so let's think about what does it take to build one of these models. The first point, and the thing I'll kind of drone on a bit about, is that it is often the case that the cross-sectional and the longitudinal effects are inconsistent. So here is a picture of one here. So the cross-sectional effect, if I just were to fit a regression slope to a bunch of data, it would look like this. But if you then also had the longitudinal profiles for each, you had enough data to actually reliably fit curves, fit slopes for each individual, you might see that this slope is changing over time. You might see this as a sort of an acceleration effect or deceleration effect. This is known as a cohort effect. It's, if you're not aware of it, and for neuroimagers, there's a really great review paper out of Norway from Sorensen, And I first learned about this from here by John Neuhaus and Jack Pavlish. So how do we deal with this? So you might, so the first thing to realize is like, why is this a problem? Well, this is a problem because if you just fit a single slope and then random intercepts, you are assuming that the cross-sectional longitudinal effects are equal. You are saying that whatever this effect is, that the effect of aging 10 years is exactly equal to the effect of comparing two different individuals who happen to differ by 10 years. And that is a strong assumption, and I'll show you evidence why that might not be. Now you might say, well, okay, well, this is a linear model. What if I did something smarter? What if I were to use, like, say, a gate-generated additive model, and that must be better? Well, actually, no, because again, these are still all the same slopes here. So that is, you're still assuming that the cross-sectional and the longitudinal effects are the same if all you're doing is adding a random intercept and you just have this one common effect of age here. So what can you do? You need to separately consider the cross-sectional and longitudinal change. So this is the first piece of evidence I want to show you why these things might be different. This is a nice piece of work that came out of Andrew Zalewski's lab in Australia. They looked at the UK Biobank. Now, so let's just take total gray matter volume in the UK Biobank, and if you just plot all the data all together, and then you can do even, do like GAN LSS, and you can see this. You don't need to do something fancy. You can see that there's a change with age, a difference with age, and it seems to be getting a little bit steeper. Now, of course, because in the UK Biobank, we also have 2-point measurements, you can also, there are, of course, sophisticated things you could do. These people were not statisticians. They said, listen, we're just going to compute the rate of change within each individual. Just very, very simple, no statistics, really just the measurement at scan 2 minus the measurement at scan 1 divided by their difference in age. So now we have these two different measures of expressing sort of the effect of age and or time. And what they found is that when you then put splines through these two different things, so this blue curve here is just the spline fit to this longitudinal change data, and this red curve here is just the derivative of this line here. And you can see that actually, of course, these are all negative because they're going down, and actually they're actually changing because this is actually has a slight curve here, but they are different. At the youngest age, they seem to be consistent, but for the older ages, you see this inconsistency that basically that there is a difference in the cross-sectional effect of age between individuals and the longitudinal effect of how you change, how one single individual changes with time. So this is really sort of driving it home, the different things might be going on here. But I do have to take issue with this paper because they said, maybe there's like a sick volunteer bias, and maybe it's these people who volunteer, are sicker and hence they're getting worse quicker. And I think they've got the complete wrong end of the stick. So here's a toy illustration to show why it is. Let's say things are really simple and they're the way I said they aren't, which is that all the change, the longitudinal and the cross-sectional change is consistent. Right? But now let's be realistic and say, actually, eventually people die, or the people who are most frail and ill are not going to be able to come back. So but who are those people? Well, it's the people with the worst brain health, and perhaps the people that have the lowest gray matter volume. So that means we're losing these individuals down here selectively. Now I'm exaggerating this, but this is an example of not missing at random, missing data mechanism. And what is that going to do? Well, of course, that's going to shift up the apparent cross-sectional effect, but yet still preserve the longitudinal effect among those who we can measure. So, in fact, I think this is a much more parsimonious. This corresponds to what is the well-known and well-documented healthy volunteer bias of the UK Biobank. And in case you don't know, the UK Biobank, the 500,000 people, are already healthier and wealthier than the UK population as a whole, and it's been documented that the imaging subsample is yet healthier, and it's probably the case that the people that come back for 2 visits are yet healthier. So I think a much more parsimonious explanation that there is a healthy volunteer bias, but this is just pointing out and driving home that there can be discordance between the cross-sectional and the longitudinal effects, and you need to treat them separately. Okay, so how do you do this? Well, I want to say that Mandy very graciously referenced one of my papers as the origin of this, but it's this Neuhaus-Pavlish paper, and if you look back, Tom Lewis was writing about this in 1986. So this is not a new thing, a new topic. Kalpleish and Neuhaus and Kalpleish recommended basically splitting it up by taking the average effect for each subject and then creating residuals within each subject. So in the case of age, you're going to have a pure cross-sectional variable, and then you'll have a pure longitudinal variable, which are basically the residuals of aging or time for each individual. But it turns out there are other ways you can do it. For example, and I find my collaborators are more comfortable with this one, which is that you use baseline age for the cross-sectional variable, and then you use time or age elapsing from baseline for the longitudinal variable. These are going to give you the same sort of significant same fit, but I think some people might find this easier to interpret. And so this is all, you simply take any time varying variable and you split it into these two, one pure cross-sectional, one pure longitudinal, and that is going to give you this flexibility. And of course, you can even do more flexible things. And this is nicely reviewed in the Sorensen paper. You can separately take up the issue of modeling the cross-sectional and longitudinal effects. It is certainly the case that you generally will have more information about the longitudinal effects, the cross-sectional effects. I mean, you get multiple scans, you get multiple measurements and nail down that cross-sectional effect on each individual. Whereas longitudinal, especially if you just have 2 points, you just have this noisy difference kind of that's nailing it down. So you might do things like saying, I'm actually going to consider a flexible cross-sectional effect of age, while just sort of having a linear effect here. But of course, also I could also contemplate doing an interaction here. But you see there's no quadratic effect of age. I've completely and separately taken up the question of how am I going to best model the cross-sectional and the longitudinal effects. And in general, you can afford more complexity in the cross-sectional effects than the longitudinal. And just to say, this is an example of modeling basically an acceleration effect. As people are older, you're getting a change in the change, basically. And they focus on calling this a cohort effect because you can't really distinguish between these sort of age and cohort. Okay, so that's just kind of some basics that maybe you're well familiar with if we used longitudinal data before, but it's something to keep in mind. It does not, this sort of a wisdom does not just apply to age. It applies to any time varying variable, but in my experience, it's most beneficial for age. In other variables, it doesn't add anything. But there isn't evidence for inconsistency, or simply if it's a very weak effect, you'll struggle to get significance on the longitudinal effect just because it's more, you need more data, you have less power to detect longitudinal effects. And so you can help yourself by making an assumption that the cross-sectional and the longitudinal are equal, and then just modeling it as usual as one single thing. But it's wise to then be thinking like, well, that is a modeling decision that I've made, that I'm assuming that these cross-sectional and longitudinal effects are consistent. So that's all about the mean model. I'm not going to say too much about the dependence model, just to say that usually we just use a random intercept to capture compound symmetric dependence among the repeated measurements. You can do things with random slopes. I've always been frustrated by the limitations of LMER. It's a very basic thing. It's hard to do anything more complicated or add structure dependence on the random error. But if you look at NMLEs, LME actually has much more flexibility. In nice blog post that can help you set that up. Okay, so now let's get to actually, because of course, so far I haven't talked about neuroimaging pretty much. So let's get to practical tools for neuroimaging data. This is recording it, but this is not. Right, so people might be familiar with this package called SPM. So it does say that it has very flexible modeling of repeated measures covariance, and it is true, it does have that, but it makes the assumption that that dependence is the same over the entire brain, which is a very restrictive assumption, and I don't think that's really realistic. FSL features a method that is pretty similar to a best practice mixed effects analysis when you just have one measurement per subject, because it actually uses the standard errors from the first level models, but it doesn't really have any good way of dealing with multiple measurements per subject. Of course, AFNI does a great job by wrapping to one of the best practice tools on LMER, and it's something called 3D LME, so that fully deals with it. And FreeSurfer also has some tools to do basically a spatial temporal modeling. So they actually do some spatial regularization of these longitudinal effects within parcels. And there's some other projects out there that maybe you're less aware of. There's another R wrapper out there, and people at Penn have developed something called Voxel, which is another wrapper. But what I want to talk about are three packages that were developed specifically for neuroimaging from the ground up. So the first one is SWE, and that was motivated by a sandwich estimator approach. So when I first got into longitudinal neuroimaging, and if I just kind of opened up the SPM manual, and if you had longitudinal data, this is what it would tell you to do. It would tell you to use these dummy variables, so basically to fit the fixed effect, fit subject intercepts as fixed effects, which is, aside from just being wrong from a statistical approach, it creates these monstrous design matrices. So I actually have two effects of interest here, the intercept and the effective time. And then I need 600, 817 dummy variables. And the other thing I'll stress on this ADNI data here, of course, is that ADNI is very imbalanced, and that's something we do not want to assume that things are balanced ever. That's just really restrictive. There are actually some structural imbalances here. They simply did not follow people that had AD or animal controls at 18 months or 36 months after AD. So that's something we definitely want to be able to deal with. So what can we do instead? Well, instead we can say, well, why don't we just fit a marginal model? So of course, do not use those subject intercepts, but then you need to deal with that dependence. And of course, the marginal model, also known as pseudo likelihood or generalized estimating approach, is to say, yes, fit the wrong model, but then work out the standard errors that account for that dependence. And so that's the approach to be taken. And given the computational intensity, and certainly when we were doing this earlier, it was almost 10 years ago, it wasn't really computationally, it would be very computationally intensive to deal with a nonlinear optimization. So we simply used our working covariance with independence. We fit a OLS for a marginal model, and then we use the sandwich estimator here. So to me, it's like amazing that the sandwich estimator works, because this is a rank 1 covariance estimate in the middle of the meat here, but actually, it does work. But of course, does it work? Well, because of course, sandwich estimator, anyone who's used these methods knows these are asymptotic methods, right? And if you went to some biostatistician and say, oh, I've got 50 subjects and I want to use a sandwich estimator, they might say, no, crazy, that's not enough. So what I thought was going to be like a quick and easy paper turned out sort of long extended chapter in my student's thesis to figure out what was the right combination of these different pieces of the puzzle. What were the right type of residuals to feed into the rank 1 covariance matrix, and also then it'll also address the issue of coming up with effective degrees of freedom, which is another thing you picked up in another chapter, which I'm not talking about. So we found that for the sample sizes that we were countering in neuroimaging, using this standardization with the 1 square root of the leverages was the right thing. And then of course another thing we did, which is basically makes this not properly a classic fixed sandwich estimator, is that we found we needed to pool this V over subjects. So if we wanted this to work with, unfortunately, the common sample sizes at the time, we had to pool this over subjects. So this is not the classic, you cannot, the classic one assumes that the variance can be different for every subject, right? That's a classic sandwich estimator. You make almost no assumptions on the covariance. We are making the assumption that the covariance is the same over subjects, but these combination of these two things got us to have valid false positive rates down to 20 subjects per group, which was important for a lot of the use cases, even though the ADME data here, of course, has many more than that. So then how do we get inference? Now, of course, because this is no longer a proper linear model, we can't use random field theory. So we just used either voxel-wise uncorrected p-values that we could then feed into FDR. And of course, also, you cannot do permutation in a repeated measure setting, because what's exchangeable? Under the null hypothesis of some effect, well, that's still, you're going to have dependence. So we took a wild bootstrap approach where we make residuals, and then we multiply each subject's residuals by 1 or -1 to make synthetic data, which we then refit to the model without the effect. It turns out there's also, as people might know, there are many different ways to do bootstrap inference and p-values, and Brian Guillaume evaluated all these and came up with methods that seem to work in our context. So with that, we can then get uncorrected p-values that are corrected for the family-wise error rate with a max statistic approach, as well as cluster-wise and TXC inferences. So this is just a quick demonstration with the ADNI data. At the time, this was using data that Paul Thompson had created. I think this was after Wes, he found his bug with his longitudinal data, which Wes Thompson discovered. And so we're going to fit a model that has 3 intercepts for normal control AD. We'll fit the cross-sectional effect of age by group. I'll fit the cross-sectional, I'll hold this visit. Again, this is the intersubject, this is each person's age centered by subject. And then I'll also do the acceleration, the product of these two. Now, the first thing to do, if I compare, and this is a little bit fraught, I'm almost reluctant to show this, if I just compare the naive OLS to the sandwich estimator, well, of course, it looks better. But of course, we know from simulations that these inferences cannot be trusted. These inferences are inflated here. But we do get something sensible from the sandwich estimator effect. But my most favorite thing is when we surfed around, we could find 2 different patterns. In some areas of the brain, for example, in the anterior cingulate, we did find consistent cross-sectional and longitudinal effects. Here shown as the big thick line is the cross-sectional effect, and then the longitudinal is these little tick marks. And remember, we fit an acceleration effect, so they don't have to be, they can actually not only be different, but they can actually change in their rate. But then here in the right posterior cingulate, one of the areas that shows decline with Alzheimer's disease, you see, and this I think is really cute, the healthy controls are actually showing rather consistent cross-sectional longitudinal effects, but the MCI and the AD subjects are showing quite discordant. In fact, actually, there's hardly any cross-sectional effect of age here, but the individuals who are 65 and have Alzheimer's are showing this rapid decline, and notably, that decline is getting less severe as you go on in age. And when I first saw this, I thought, this is crazy. How could it be that older people are who have AD are actually declining at a slower rate? But once we talked to Paul Thompson and other experts, like, no, look, think about it. No one gets Alzheimer's disease for 30 years, right? So these people here are sort of, people who get Alzheimer's around age 60, 65. These people who have survived all the way to be 85, those are really different people. Don't know how, there's something special. They actually survived not getting sick until finally getting diagnosed with Alzheimer's. And they probably have some very resilient brains. And they're they're losing brain volume at a slower rate. So just another example of how these things can be discordant. It can be concordant or discordant, and it's really important to treat them separately. This framework lets us do that in a very computationally efficient way. And the other thing that Brian Guillaume did, which was great, is that he embedded this into SPM. So SPM now has a toolbox called the SWE toolbox, and one of the last things he did before he left my group is that he then implemented support for SIFTI surfaces, SIFTI and HIFTI surface data, so that it makes this accessible to people who use SPM. Okay, so that was the first sort of foray into this, and then I got another student, Tom Mallon, who I asked him to take up this basically fitting proper mixed effects models. So what's the motivation there? So the sandwich estimator is fast, but it's not optimal, right? Because I'm fitting an ordinary least squares model, and we know, of course, the other reason there are 2 reasons that we need to use a linear mixed effects model for dependent data. One is to have valid inferences. The other is efficiency. We know that the optimally efficient estimates come from fitting a linear mixed effect model that actually accounts for the dependence. Now, LME4 is a remarkable tool, and it's gotten better. Actually, when we first started developing the work for SWE, we were showing that LME was not converging on all these different data sets, and we're really excited. Oh yes, SWE always worked. And by the time we got to publish SWE, we couldn't break LME. It had gotten that much more robust in the early 2010s. Still, it's not fast, and unlike LM, you might know that in LM, you can put in a matrix for Y, right? So you can do a mass univariate analysis in LM, and it's pretty fast. In LME, you can't do that. You can only do one response at a time. And there's nothing slower than doing a for loop, and there's basically and the reason for that is that you're not able to exploit the vectorization. Basically doing all the modeling in one, fitting in one go makes a tremendous difference. So I challenged Tom to say, okay, do a proper linear mixed effects model that actually is vectorized. And so what he found out is that actually we wanted to do this in Python to integrate with our computing environment and other colleagues. And it turns out that the Python, that LME works because of some incredible sparse matrix libraries that Doug Bates created, and they just didn't exist in Python. And maybe that's changed, but even things that said they were supposed to work didn't work as they were supposed to. And it was really, so it continues to be, I continue to be impressed by how there's some things that we just come to expect in R, and they're just not there in Python. The other thing is that he basically has built it to be able to be parallelized with a SGE or Slurm so that you can feed in arbitrarily large data sets. So the key to scalability is a two-step process. So we have a summary statistic computation, which can be parallelized, and then a parameter estimation, which can be parallelized by blocks of different subjects, and then a parameter estimation stage that can be parallelized by blocks of space or slices or what have you. And the other thing that Tom developed is that actually for the standard linear mixed model, fixed effects X, random effects matrix Z, possibly D covariance for the random effects, that the sufficient statistics for this model can all be written as cross products. So this was actually important to one of our collaborators because he wanted to do a federated model where he could fit a linear mixed effects model, but on data he wasn't allowed to share. That is, he had different sites, like some of the sites like in India could not share their imaging data. But if we could ship off a portion of a design matrix that they could compute inner products with and send out those inner products, that would actually fit with their data governance issues. The other thing I'm very proud of Tom, and I didn't set him on this in particular, he noted that when he used what everyone else used to find the approximate degrees of freedom, the effective degrees of freedom, LMER test, it was really slow. And so we need to do this because whenever we're doing tests of some contrast, we need to know what is the effect of replacing the variance sigma squared and the random effects covariance D with their estimates. And what he found is that they were doing numerical computation of the gradients, but if you're handy with the VEC-H and VEC formulations, you can just grind through and find the exact expression for the variance of the contrast, excuse me, the variance of the standard errors, and the necessary gradients to implement a delta method. So Tom showed in his work that actually his effective degrees of freedom were not only faster, but also had much smaller mean squared error than the ones that came from LMER test. And I'm not sure why they didn't just do the same implementation. Maybe they had something more general, but this is something I was very, very pleased with. So this is a reference to the federated analysis. I'll just skip this. If anyone knows Vince Calhoun, this is his project, CoinStack. So now our LME, big BLMM is implemented in the CoinStack distributed data analysis tool. Okay, so this is just some results showing the effective time of comparing fitting a loop. So just to confirm that, yes, indeed, for whether it's fitting a fixed or a random effect or a random effect and random slopes, our model fitting is substantially faster. And of course, you might wonder, how can this be flat? Well, of course, because we can take advantage of parallelization. We can actually use lots of nodes and hence be much faster than LMER. And then this is just an example in the UK Biobank task effect. And so we have, just for reference, the anatomy, and then we've got, is there evidence for random intercepts over none? Well, yes, of course, but not everywhere in the brain. You actually, if you had to, if you were doing a voxel by voxel model fit, you would probably say, yeah, in white matter, there isn't evidence for a random effect. It's fine. But where there's activation, oh yes, there's definitely need for random intercepts here. Now, is there need for random slopes? Yeah, not so much. And here's an estimate of the actual effect of interest. And then this is one of the things I love about mixed effects models is that you break down what otherwise would just be one glommed variance into a residual error that's just about the measurement error, and then the pure between subject variation. And this is really interpretable. So what is the source of residual error? Well, a lot of it is the variation around the edge of the brain, attributable either to subject motion, which was just impossible to perfectly correct, or imperfections in the image registration, inter-subject registration. Whereas what is the source of variation between subject? Well, that's only where we have task activation. So this is just a nice, and normally if you just had a cross-sectional data set, those two would be mushed together, and you would get the superposition of those two. So that's a nice thing that we don't get from the SWE, but we get here is that we can actually see the two different sources of variation. And the other thing that Tom implemented, which is really important and surprisingly is not supported in SPM or FSL, I'm not sure, I think AFNI does deal with this, is varying degrees of missingness. So in SPM or FSL, if you have any missing subject that at a voxel, that voxel is kicked out of the analysis. So for the UK Biobank, all these voxels on the right here would have been NA. They're just gone in FSL or SPM because there's one or more subjects that are missing. And Tom supported variable missingness up to, I think, well, you can set the parameter. I think we use 50%. And so we have results over the full grain on the left and not including these voxels here that would otherwise have been lost for missing. Okay, and the last piece of work I want to talk about is work that was done with Andres Dale and Wes Thompson, FEMA. So this is fast and efficient mixed effects analysis. And so what's the motivation for this? Well, the BLMM is definitely faster than looping over LMER, but it's still not super fast because it is still optimizing. It is doing optimization with vectorization. We're updating all the voxels together in a group, but it's still iterative. And so Anders thought we should be able to do better than that. So here's the crux of the problem, of course, is that, one of the things that's amazing about OLS is that it is just lightning fast. I mean, I remember one of the first things I did when I worked at the Pet Center, I was like, I'm going to fit my own regression tool. And I was really disappointed to find that I could not write C code that was faster than MATLAB. Because, if you're doing matrix multiplication in MATLAB, it's using BLAST, like you can't go faster than that. And this is all OLS is, right? It's a matrix multiplication. So this is lightning fast. Now, for a linear mixed effects model, we have this problem that we need. How do we get our estimates here? Beta hat. Well, you need to have whitened estimates written here. So the X star is the whitened model. The Y star is the whitened data. And in red, I've highlighted the V, stressing that this whitening is different for every single voxel and for every single voxel. And so that is a problem that was a difficulty that Tom overcame in his work, but it's still just it's a pain, and you have to update these each. So there are two tricks that FEMA uses. So the first one was avoiding the iterative optimization by using covariance regression. So actually, Martin's no longer here, but of course, back in 2012, Martin Lindquist published a paper using the same method to estimate variance components. And there's been a nice paper in JASA by Zhao et al. That sort of putting this in a sort of formal framework. But here's an illustration. If I have a 3-visit random effects model, repeated measurements, of course, I have a random, this is the random intercept, which gives rise to a compound symmetric dependence, and then the random measurement error. Now, if I'm using maximum likelihood, I need to iteratively optimize this with these two sigma V and sigma E inside the sigma. The idea of covariance regression is you simply consider all possible pairs of the error and their expected value. It's basically like a method of moment approach. What is the expected value of the first one squared? Well, it's the sum of beta B, sigma B squared and sigma E squared. What's the expected value of this, of any pair that's of the same individual? Well, that's just sigma B here. And so you can set up a linear regression. A linear regression has many more rows than your original data, but still it's a linear regression, and hence you can very quickly estimate these variance components. Okay, that's speed up number one. And then the second speed up one is that given that Anders was motivated by the ABCD, where we have thousands or 10,000 subjects, it's not a crazy thing to standardize your data so that the variance is, all the voxels have unit variance. And if that's the case, then actually we know that our variance parameters are bounded. They have to be between 0 and 1 on both ends, and hence admits a binning strategy. So basically what we can do is do the fast covariance estimate with a covariance regression, and then to avoid having to whiten every single voxel individually, we will put we will basically quantize the variance parameters so that now instead of having number of voxels whitenings, we only have number of bin whitenings to do, because we can group them as a whole, again, exploiting some vectorization. So does this work? Well, again, using the ABCD data with about 1,200 subjects, We had 1,100 subjects at baseline. It's almost 8,000 two-year follow-up. We applied this model to cortical thickness and surface area. And now with this, we have a lot going on. We've got, because we have both siblings and twins involved in this, we can actually model random effects due to additive genetic variance based on similarity of either 1 or 0.5 for 1 for identical twins, 0.5 for dizygotic and siblings. We have a common household effect, so we can, again, it models the dependence for anyone who's coming from the same house. Of course, we have multiple measurements per subject, so now we have a subject effect, and then finally a random questionnaire. So we have 4 different random effects that we can estimate. And so the first question is this discretization approach sensible? And the fact is, if you get enough, yeah, it seems to be fine. We actually get negligible mean squared error after about 20 bins or so. And we are finding that we're getting basically the identical estimates we'd find if you'd done the true values, and also very similar, not shown here, but to if you'd done a standard LME. And then here's comparing the computational time here between the using R method FEMA down at the bottom here and fit LME. Again, if people don't know, actually, at this point in time, MATLAB has a work-alike LME implementation. It really surprises me. It's actually quite easy to use. And yeah. Anyway, so this lets us do things like look at the effects of age, and more interestingly, we can also look at these different variance components. We can look at the additive genetic effect. This was, to me, a bit of a surprise that there's very little common environmental effect. The dominant effects, at least in cortical surface, were in the additive genetic effect. And then also there's substantial subject effects. And of course, the other thing is that these are all sort of partitioned when all the variance has been normalized to 1. Very important to pay attention to what is the actual total residual variance, so you have some idea of how what is the total variance that's being broken apart by these two. Okay, I think that's everything I wanted to get through today. So the main takeaway was that longitudinal data, of course, is different. You need to account for it. Disappointingly, the standard neuroimaging software cannot accommodate this structure very well. There are some tools out there, but I said this talk telling you about 3 different packages, efforts that we're working on using either a fast but not necessarily optimally efficient method that now has a nice implementation in SPM, BLMM, which is much more efficient and probably one of the fastest ways of doing a proper linear mixed effects model on images, and then FEMA, which has some shortcut but seems to be a pretty accurate compromise for anomaly. I'll stop there. Thanks for your attention.
Thanks, Tom, for very well controlled time talk. Questions? John.
Can we talk now?
Yes, you're allowed to talk.
Tom, that was a very nice talk and a very important problem. But I just want, you brought up the issue of missing not at random because of patients getting sick later in life. Any ideas what we can do about that?
Yeah, question is what to do about not missing at random. I haven't taken that up. So I have certainly I have one student working on missing data, but not the gnarly issue of not missing at random. And it's something that I at some point, okay, if the people don't come back, we could think about what's the counterfactual, but at some point, they're not coming back because they're dead. So do you want to have a counterfactual analysis of what dead people's brain volume would be if you could get them back in the scanner? I don't think so. So you somehow just, and this came up in the Huntington's talk as well. So I think you just have to, we have to just know that when we're interpreting it, that some of this, it is a description of who came back and who was available.
Some of their slides looks like the residuals. Do you assume it's the variance covariance matrix is identity matrix? Do you make that assumption?
No, I mean it's as so in this case there's structure due to people being measured multiple times. There's 2 visits. There's structure because some people are related. There's structure because some people grew up in the same house. So that's all captured by the. I mean, so basically, I had the toy example here where there's just 2, but actually the model I showed actually had 4 of these covariance matrices that we then unwound as part of a covariance regression approach. So
another question is that the age looks like your model is either linear or quadratic. Why not make it more generic?
Yeah, you could, you can use splines, yeah. I mean, well, I think, this is my own little thing. I haven't like formally assessed this, but my sense is that once you're into thousands of subjects, you don't really need to do smoothing splines. You just need some judicious, like pick 2 knots, 3 knots, and that's generally accounts for all of the bendy. We all should be doing that. We should all be doing the splines, but I don't think you need to have smoothing splines. And so if you're not doing smoothing spline, you can just chuck it into your regression. And so it's basically just like what I had here, where I illustrated you could have 8 squared, but yeah, you could have like, 3 or 4, spline components here, and that will give you the nice flexible bending. Because yeah, we know over a large age range, you should not be using polynomials, you should be using splines.
Yeah, I think just like Anthony, just model the whole brain volumes. And actually you see all other ROI volumes. I mean, in many cases, because the different subject in different group have totally different patterns. And sometimes what I see is basically the data is very fluctuated when longitudinally. And could be because the imaging processing pipelines and have the issues. And that's one thing. So when I do is even like a simple data analysis, I observe that. And some subjects is more like a flat, like this. Some subject, okay. And I think that we may need a more flexible modeling strategy to handle that, such as you impose some like a monotone.
Well, maybe. I mean, one of the things I love about the SWE approach is that you make no assumption on the dependence. So like, you never have to worry about random slopes versus random intercepts in an SWE approach, because you have an unstructured covariance and whatever structure is there. I know exactly what you meant. Like if I'd actually plotted the real data here, they'd be like all over the place, up, down, left, round, But this is why we have big data to learn about the trends. So I'm not sure what to say, because I mean, we have this issue when we have this big project with Novartis, and we have thousands of subjects. And guess what? When you have 10,000 subjects, you're going to see weird stuff. And there's only so much time in the world to kind of study each one. So I don't know. I think there's a lot to be learned from the average of those things, but I'm not sure. Yeah, what's to be gained from all the ideal thing would be finding the variables that explain that heterogeneity. Yeah, I'll give you that.
Another thing is because for most older subjects, they passed away. And the trajectory that we overturned is because of this is a bias, because of that effect. There's a lot of dropout effects at the end.
Yeah, and I've thought a lot about that, and I don't know what to do. But I mean, you don't want to, it doesn't make sense to be thinking about the afterlife.
No, it's because you need to correct the bias, because the trajectory you have observed basically at the end of this kind of design is basically all these like more normal subjects in certainty.
The ones that are aligned, yeah.
Yeah.
It's very normal.
Yeah.
So you talked about how in older adults in the UK Biobank, you have this selection bias where they die off or they get too ill to come back. But in your last paper, you were talking about using the ABCD data set. And I was wondering if you saw similar like differences in cross-sectional and longitudinal effects, or if not, what do you think?
I might defer to Wes on that about the sort of the impact to which people have not been coming back. I mean, we're always worried about that, as the people with the worst SES or the people that don't come back. I don't know whether we.
I'm not worried about that, to be honest. Especially if you're controlling for like sociodemographic covariance. So, I mean, in terms of like different like informative missingness.
That's kind of the idea, yeah.
I'm actually not that worried about it, to be honest.
Because
So this might be less of an issue.
Because I think maybe I should be worried about it. No, I mean, I just I think like once you control for like the key sociodemographic variables like race and income and education and stuff like that, that you can do we actually just did a paper where we examined the 3 different ways of assessing missingness, like imputation, full information, maximum likelihood, and weighting. And they all give very similar answers to if you just put those covariates if you put the covariates in the model. So not to say that we're not measuring something that's not causing informative missingness, but they don't seem to add anything over just adding in covariates in the model for associations.
other questions?
There's a question on Zoom, I think. Can you unmute yourself, ask question, or let me just.
Hey, Tom.
Yeah, Fernando's
This is
question.
Fernando.
Oh, hey, Fernando.
Hi, very nice talk. Thank you very much. Just sharing my experience with mixed effects models when there's large population and also large heterogeneity. One fix that that I've seen is that we can do subpopulation. So we do clustering within this large population. So condition on males, condition on gender, conditioning on ethnicity, and within that, one can produce smaller subpopulations and then do mixed effects that way. So there's a bit, you control this too large heterogeneity. Do you think this is feasible? It seems like with very large data sets, we'll have enough data to produce these subpopulations.
Yeah, I think in general, whenever you have big enough data sets, you have the opportunity to segment. I mean, it's always, whenever you combine, you're making assumptions like common variants, common trajectories, and whenever you can segregate. And it always surprised me when I work with epidemiologists, that's their first reflex. It's not, don't include an age effect, don't include a gender effect. No, split your analysis by males and females and then look at it. And the only downside to it is if you then are trying to make direct comparisons between those two groups. So as long as you're not trying to so it's definitely for understanding what's going on, definitely, yeah, if you can afford it, stratify. But I think when you actually then are trying to make actual inferences like, what is the effect of ApoE or whatever, then you probably are going to want to pull everything together and get the maximum power. But definitely for understanding what's going on and, in a way, kind of the diagnosis, yes, that's a definitely good idea.
Yep, thank you.
So you have permutations implement in your SWE.
Wild bootstrap, yeah.
I can do the same for the other two, or you already done?
Oh, I didn't mention that, sorry. Yeah, so it's wild bootstrap for the FEMA tool and for, we haven't yet, unfortunately, Tom Mallon has gone on and taken faculty position, so he's more interested in random field theory. So we haven't implemented the wild bootstrap for the BLMM, which is also would be very computationally intensive, right? Because then we have to refit, but that's a good point now. So right now for the BLMM, we only have parametric inferences fossilized.
More questions or comments? Tom? If not, we conclude this session and thank you all. We have more time for capital.